Hello, everybody. So we're going to pick up our lecture sequence with Chapter 3, Section 5. So we'll call this Lecture 3, Part 5. And the topic will regard another technique for taking derivatives. This is called implicit differentiation. Now, suppose I give you an object like this, say the circle of radius 5 centered at the origin. So consider this figure. All right, now go way back to the time when you took geometry in high school and you were talking about tangent lines. So suppose I have a terminal point here that I'm putting a green dot. And the question is, of course, what is the equation of the tangent line to the circle at this point of tangency? Now, in high school geometry, you could not answer this question. And if you haven't had calculus before, you still can't answer this question until today. So now, let me show you how you can calculate the equation of that green tangent line very easily. So we start off by saying, okay, what is the equation of this circle centered at the origin? Well, it's x squared plus y squared is equal to r squared, which is 25. Okay? And so we know we have to calculate the coordinates of this point. And so whatever that happens to be, say, let's suppose that it's, say, we let theta equal, we let this subtending angle right here, say, 30 degrees. Okay, so the abscissa of the point would be the cosine of 30 degrees. So in this case, the coordinates of P would be the cosine, actually 5 times the cosine, sorry. Five times the cosine of 30 degrees would be the abscissa, and then the ordinate would be 5 times the sine of 30 degrees. Okay, and so that would be, what, 5 times the square root of 3 over 2, and 5/2. So those would be the coordinates of P. And so then the equation, well, so you could do that in trigonometry, and then you would just write y minus 5/2 is equal to the slope times x minus 5 times the square root of 3 over 2. And you could never get the slope until today. All right, so what is the slope? Well, the slope is, what is m? Okay, so m is the slope of the tangent line to the circle. So how do we calculate m? Do as you've always done. Take the equation, take this equation, and differentiate all of the terms by x. Okay, that's all you have to do. So the derivative of x squared with respect to x is 2x. Now the derivative of y squared with respect to x, we'll have to use the chain rule. So that would be 2 times y times the derivative of y with respect to x. That comes from the chain rule. And the derivative of 25, well, with respect to x, well, the derivative of a constant is 0. Okay? And so this is your slope. So solve algebraically for your slope. So we're left with dy over dx is equal to negative 2x over 2y from algebra, which is equal to negative x over y. And that would be evaluated at the point of tangency. So that would be 5 on the square root of 3 over 2, 5/2. Okay, and so when we plug that in, we get negative 5 on the square root of 3 over 2 divided by 5/2, which is just equal to the negative square root of 3. So that's the slope. What's the slope of the tangent line to the circle at P. So just plug it in. So y minus 5/2 is equal to minus the square root of 3 times x minus 5 times the square root of 3 over 2. All right, so now you have the tools to calculate the equations of tangent lines to circles. So let's see, let's consider another function, another example. X cubed plus y cubed is equal to 6xy. And we want to calculate y prime. Well, again, just differentiate each term in this equation with respect to x. So do this. Differentiate each term in the equation with respect to x. Because we know that the derivative operator is distributable when you have is distributable with respect to a sum of functions. So simplifying, we have 3x squared plus, use the chain rule here, the power chain rule. So we have 3y squared times dy over dx. And then here we have to use the product rule. Okay, well, we have a 6 constant, so we can take the constant out. And so this would be x times the derivative of y with respect to x plus the derivative of x with respect to x times y. Okay, so simplifying, so we have 3x squared plus 3y squared y prime is equal to 6 times x y prime plus y. And now all we do is solve for y prime algebraically. So 3x squared plus 3y squared y prime is equal to 6xy prime plus 6y. So move all the y primes to the left-hand side of the equation. So we have 3y squared y prime minus 6xy prime, and move the non-y prime terms to the right-hand side of the equation. Will be minus 3x squared plus 6y. Okay, factor out y prime. So it'd be y prime times 3y squared minus 6x is equal to minus 3x squared plus 6y, and then solve for y prime. Okay, divided by 3y squared minus 6x. Okay, so that's the solution. That's dy over dx. And that's how we calculate the derivative implicitly. Because where does implicit come from? Well, it originates from the fact that you have a multivariable function, x and y. And when you use implicit differentiation, you're invariably going to have to invoke something like this, the chain rule, so that you can extract out dy over dx. Okay, so I think it's pretty intuitive how to do that. But what is the utility of implicit differentiation? Well, it's useful for calculating the derivatives of inverse trig functions. All right, so that is the important part. Implicit differentiation is used to calculate the derivatives of inverse trigonometric functions. All right, so before we proceed, I need to brief you on what's meant by the inverse of a trig function. So let me pull up an internet calculator. So let's insert a web tool, a web browser, and go to our calculator. So des most. Okay, so let's consider the function y equals sine x. Well, let me set my window properties first, right? So I'll use radians, and we'll have the x-axis labels in terms of multiples of pi. So y equals sine x. So as you can see from the sine function, as shown in red, oh, I just lost it. Let me put it back in. Now it's shown in blue. As you can see, the sine function takes many inputs, okay, and it maps it to a single output. So for instance, if I were to zoom out, looking at the graph of the sine function, you can see that there are many input values, okay, that produce a single output of 0, and so forth. So the question is, I pose to you is, sine x is not 1-to-1. And you can tell by the graph. Many inputs map to a single output. That's not 1-to-1. You have a many-to-one. So the question is, how can you have an inverse of the sine function? I mean, it's on your calculator, right? How can you have an inverse sine? Because to have an inverse of a function, an inverse, to be able to get to an inverse exists only if the function is 1-to-1. Which the sine function is not. Yet you have an inverse sine function on your calculator. So is the calculator wrong? Okay, so we have a dilemma here. So when we talk about the inverse sine function, we don't mean that we're taking the inverse of this. We are not taking the inverse of this. Instead, we're taking the inverse of a special function called the principal sine. Okay? We take the inverse of a principal sine. So let me see if this calculator supports the principal sine function. So let's zoom in. Let's see if it's smart enough. I haven't checked this yet. So the principal sine function is usually written using an uppercase x, like so. And it doesn't appear to support it. Okay, so what I'll do is I'll show you the principal sine function. So here, the blue, what's shown in blue is the sine function, and the principal sine function is found by truncating the sine function on the interval 0 to 2 pi, which I'll accentuate in red. So if we were to take this piece that I'm showing in red, right here, this is called the principal sine. And it's written using an uppercase S. Okay? Now, if you notice that this red piece goes through the full range of values of the sine function. Its range is from -1 to 1 and all numbers in between. So here's the range of the principal sine function. So it is also 1-to-1, as you can tell. Okay, it's 1 to 1. Well, it's not 1 to 1, is it? No, because it's not 1 to 1 because it fails the horizontal line test. So this is not true then. This is not the principal sign. So we need another variant. So this is not invertible because you can see that many inputs, in this case 2 inputs, map to a single output. So this isn't 1 to 1. So this is not the candidate for the sign function. So let's see. I have to look for something else. That was not right. So how about we use this piece as the principal sign? Yes, so I think we're good here. Yeah, this portion that I'm accentuating in red will pass the horizontal line test. Remember, if a function passes the horizontal line test, then it's 1 to 1. That's you may remember that from algebra, the horizontal line test. So this, we'll call this the principal sign function. Okay, accentuated in red. And again, it passes through its full range, the full range of the sign function from -1 to 1 and all numbers in between. Okay, like so. And each value of x between -pi and pi produces a distinct output. Yeah, so in this case we can take the inverse of this curve in red. So we will call this the principal sign function. All right, so it will have an inverse. And so let's see if we can see if this graph is smart enough to plot. Y is equal to arc sine x. All right, and so that'll be shown in purple if it works. Let's zoom back. Zoom out. Zoom out. Zoom in. Okay, so let me erase the red piece. All right, so the purple piece is the inverse of the principal sign piece. Okay, so remember, the principal sign is this piece right here. Okay, and then the inverse of the principal part I'll accentuate here. Right there. Like so. Okay, so let me erase this so it'll be more clear. Now, okay, so for the principal part, for y is equal to principal sign x, okay, we have the domain of principal sign x equal to, we can say -pi to pi, like that, so as not to duplicate output values. So this makes it for 1 to 1. And then the range of principal sign x is equal to -1 to 1. All right, so we have that result. Now, when you take the inverse of the principal sign function, the domain and the range flip, okay? So the domain of arcsine, okay, so we'll call arcsine as the inverse of the principal sign, is equal to the range of the principal sign. And likewise, the range of the arcsine of x is equal to the domain of the sign, principal sign x. Okay, so that's how that works. So if we say if say -pi0 is a point on the graph, so negative pi 0. You see that right there? That's on the graph. We would expect 0, 0 pi. We flip the, let's see, so at x equals 0, so how does this work? Okay, so what are the coordinates of this point? So that's right there. And we have 0, 0. And let's see here. Do we not have, did I not? Okay, so I still don't have the principal sign correct. That should be, yeah, so judging by the graph, the principal sign function should range from negative pi halves to pi halves. I'm sorry. So I still don't have the principal sign part right. So let me make sure that I get this right. So it actually goes this way. So let me zoom in. Sorry, I need to adjust the principal sign again so that we go through the appropriate values. So let's see, zoom out, zoom in. Okay, here we go. Oops, lost it again. Okay, hold it right there. Okay, the principal sign, I'm sorry, I still don't have it correct. It should range from negative pi halves to pi halves. Okay, like that. So there's our principal sign. So now I got it right. It's not negative pi to pi, but it's negative pi halves to pi. I was thinking of something else. So the red curve is your principal sign. It's right now. And so if we do this, all right, so if we identify one of the endpoints on principal sign, see negative pi halves, negative 1 is on the graph for principal sign. Then we would expect that negative 1, negative pi halves would be a point on the graph arc sign. And there it is. Okay, so you see how they're symmetric with respect to the line y equals x. Okay, and likewise 0, 0 is a point on both graphs. And so pi halves 1 is a point on the graph of principal sign, and so we would expect this point to be 1 pi halves. So if you ever need to sketch the arcsine function, this will be the technique for rapid sketching of it. So let me see if I can get there. I can't, it's not focusing. Yeah, it's a little bit, the hot spot is a little bit off. So yeah, it kind of ends. Yeah, it kind of ends right. So the endpoint right here would be 1 pi half. So there's a glitch with the computer. So anyway, so you know that a function and its inverse are symmetric with respect to the line y equals x. So just as an algebra review. So let me go ahead and stuff in y equals x, which is shown in orange, and then you can see that the purple and blue curves are symmetric with respect to the line y equals x. All right, so this is what we mean when we take the derivative of the inverse of a trigonometric function. All right, so let's work on calculating the derivative of the inverse sine function. So go to another page. Sorry about not being able to get the principal part right, but we can figure it out. We don't have to look it up in the book what the principal parts of a trig function are. We can just deduce it from just exploring the graph, right? So I don't keep it memorized. I just try to understand it. So if I make a mistake, I can use my understanding of inverse functions and go back and correct it. And so that's what I'm kind of drive you guys toward. I don't expect you to know offhand what the graph of the inverse sine function is, but I expect you to be able to extract it out from looking at the graph of a sine function. All right, so anyway, consider y is equal to the inverse, okay, this is red, the inverse sine function, and I had arc sine on the graphing utility. And of course, we wanted to calculate the derivative of this function. All right, so clearly, if we go back and we examine the look at the graph of the arc sine function, we need to ask ourselves, will it have a derivative, or can it have a derivative? And so let's sketch it again. Okay, so now it's shown in red. And you can tell by the graph that the function is continuous. Okay, it has no sharp corners, it has no holes, no vertical or horizontal asymptotes. So clearly, we can calculate the derivative of this function on the domain -1 to 1. All right, so that should exist just by looking at the graph of the inverse sine function shown here. So we know we should be able to do it. So now, the way you deal with it is you'll use implicit differentiation. So essentially, you take the sine of both sides. And so now here's where math gets a little bit abusive in its notation. The assumption is that I'm taking the principal sign of both sides, but instead of writing uppercase S, I'm going to be inconsistent and I'm going to use lowercase s. Okay? Because the assumption is that we're only doing this on the interval where the inverse sine function exists. Okay? So we have this, okay, and so knowing that a function composed with its inverse is equal to the argument, we have sine y is equal to x. Okay, so now all we have to, and this is valid for, only works if y is stuck between -pi12 and pi12. It only works there. And why is that? Because if we go past these values for y, then we lose our one-to-one advantage. Okay, it becomes a many to one, and we can no longer take this composition. We can no longer do this inverse composition. So we have to restrict our y range to this. Okay, all right. So now we're allowed to use implicit differentiation. So differentiating the left-hand side with respect to x using the chain rule. We get, and differentiating the right-hand side, we get 1. And so now all we do is solve for dy over dx. We get 1 over the cosine of y, like so. And now we have to replace y with its expression in x. So how do we do that? Well, we know that we can use a principle of right triangles. Okay, we know that if this is angle y, and if we have a unit hypotenuse, then the sine of y is opposite over adjacent, and that comes from this equation right here. Okay, so if the sine of y is x, what is the cosine of y? Well, the cosine of y is adjacent over hypotenuse, and so this would have to be 1 minus x squared, the square root of 1 minus x squared. And you can verify this length by the Pythagorean theorem. This quantity squared plus x squared must equal to 1. And so now we just replace y with its expression in x. Okay, so that would be cosine of y is equal to 1 minus x squared. Okay, so that would be the derivative. So the derivative with respect to x of the inverse sine function, based on our understanding of what it is equal to the square root of 1 over 1 minus x squared. Now, I don't expect you in general to memorize this, but I expect you to be able to understand how to derive it. Okay, and so we just went through the derivation. It was very logical. Just think what the inverse sine function is. Okay, and then use implicit differentiation, and you should get this if you don't have it memorized. Okay, so let's see here. Can we do the inverse cosine function? I guess we can attempt that. All right, so let's identify what the inverse cosine function would look like graphically. So pull up the graph again. The internet is slow today. Okay, so here we go. So y, let's start off with graphing y equals cosine x. So because we're trying to pull off the inverse cosine function. Understand what inverse cosine is. Okay, so shown in red, there's the cosine function. All right, so we need to identify the principal part for which we could take the derivative of. So let me set my window properties. So we want radians, and we want radians, and we want multiples of pi. No, we want this, and we want this. Okay, so there's the graph of the cosine function. So what part of this graph would be 1-to-1 for cosine, and it goes through its full range of outputs? Okay, so let's see what we could pick off here. Can we start here? Okay, and say, okay, so this piece wouldn't work. Can we start at pi halves? Can we start at 0? Let's see. Yeah, so we're trying to pick off the principal cosine function. All right, so here goes max to min, and this would be pi, right? And go to duplicate. So where does it go through its full range of values and pass the horizontal line test? So maybe about from negative pi to pi, perhaps here. Yeah, so let's see, let's identify a horizontal line test that it could survive. So if we start at here at pi, that won't work either, right? So how about we start at pi halves? That wouldn't work. Starting at 0, we could start at 0. Okay, so that wouldn't work. So let's see here. What would be a good candidate? We started here at 0. So maybe on this interval, perhaps. So if we identify this interval, that would be unacceptable as well. So, well, one thing we can do is, if we're having trouble, why don't we just go ahead and sketch the graph of y equals arc cosine x and see what the principal part is. So y is equal to arc cosine x, shown in blue. Okay, and then we can reverse engineer it, so to speak. So it appears to go, okay, so from 0 to, what is that, pi? Okay, oh, interesting. It's interesting. Okay, so from 0 to pi, we'll do that then. So from 0 to pi, there's pi halves. Here, take this off. The cosine function goes through its full range of output values. Okay, so if we start at 0, And the yellow curve, okay, so the yellow curve defines our principal cosine function. So let's parameterize principal cosine. So if we let y equal to principal cosine x, as shown in yellow, okay, so what is the domain? So the domain of principal cosine x, now remember principal cosine x has the one-to-one property. Okay, it's a one-to-one function, so that's what we take the inverse of when we say we're taking the inverse of a cosine function, we're actually taking the inverse of this yellow piece. And so its domain goes from 0 to pi. Okay? And we'll include the endpoints. And then the range of the principal cosine function, same as the range of the principal sine function, okay, it goes from -1 to 1. Okay, and so with that, we'll have the graph of the arc cosine function. So y is equal to arc cos x. Oops, I did not want to do it. Wrong tool. Okay. Y is equal to arc cos x. Okay, and that's shown in green here. Shown in green. And so its range is from, where are they, oh wait a minute, what are they saying the domain is here? It appears that the domain is different, right? So maybe I didn't get it, I didn't calculate it correctly. This is, what are the coordinates of this point? This appears to be something different here. Okay, so 1, and this should be -1, right? Yeah, -1 pi. Yeah, so 0 to pi is the, okay, so now the range of the arc cosine function, or excuse me, the domain of the arc cosine function would be -1, okay, to what? 1, right? X equals 1. So you see on this interval between -1 and 1 is the domain, and then so the range would be say what is that? Y equals pi. Okay, shown in black. Okay, so here this bounding box, which I'll show in green. This bounding box defines the enclosure for the arc cosine function. Okay, so arc cosine function lives in this space right here and nowhere else. Right there. Okay, so there's your concept for the arc cosine function. So now we want to calculate the derivative of the arc cosine function. So y is equal to inverse cosine, or arc cosine, of x. Okay, and so we'll use implicit differentiation again. So we'll have cosine y is equal to x. Okay, then we take the derivative with respect to x at both sides. So that would be minus sine y times dy over dx is equal to 1. Solve for dy over dx. So we have dy over dx is equal to -1 over sine y. And now we have to replace y with its expression in x. Okay, so we'll use the principle of right triangles. Okay, here's angle y for a right triangle, and we know the cosine of y is equal to x. Okay, adjacent over hypotenuse. And so what is the length of this side? So this would be 1 minus x squared. Okay, and so the derivative of the arc cosine function would be negative 1 over 1 minus x squared. So that's how you prove it. Okay, so easy enough. So let's move on. Let's do the other inverse trigonometric functions, derivatives of the other inverse trigonometric functions. So let's consider tangent function now. So let's calculate the derivative of the arctan function. Okay, that's next. Yeah, checking my notes. All right, so we'll start off with having to identify the principal part of the tan function, because again, the tangent function, like most trig functions, is not one-to-one. So what would be a good candidate for the inverse trig function, or the principal part of the tan function? So a good candidate for the principal part of the tan function. So let's see if we can use this graph to figure it out. So I want my radians and I want my x-axis. Okay, so all right, so let's see here. Clearly, the tangent function goes to its full range of values for this particular branch that intersects the origin. So why don't we restrict our principal part between, say, negative pi halves and pi halves. So all right, so we'll consider this piece, which is shown in red, to be the principal tan. And of course, as usual, we write it in uppercase. So the graph shown here is principal tan x, written with an uppercase T. Okay, so there's principal tan. And it should be asymptotic. This branch of the tangent function is asymptotic with has vertical asymptotes at x equals negative pi halves and at x equals pi halves. All right, so the work that remains to be done then is, so we just flip the domain and ranges of this red curve. Now, when we flip the domain and range, the output of the arctan function then would range between negative pi halves and pi halves, and so the vertical asymptotes would translate into becoming horizontal asymptotes for the arctan function. And since and then the domain of the arctan function. The domain of the arctan function becomes the range of the principal tan function. So the range of the principal tan function is the set of real numbers. And so that means that the domain of the arctan function would be the entire x-axis. Okay, shown in blue. So the arctan function is defined everywhere on the x-axis, and it's restricted by two horizontal asymptotes. The first one being y equals negative pi over 2, and then the second one being y equals pi over 2. Okay, so you can see from this graph, the blue curve is y equals arctan x, and it has two horizontal asymptotes. And okay, so that's the construction we'll use for arctan. And so now we'll calculate its derivative. Okay, so the derivative of arctan. Right, so please take note of the graph and know how to produce it. All right, so you see I'm not having to memorize anything. I'm just investigating properties using a calculator and coming up with these formula. All right, so next page. So y is equal to arctan x, which we'll say is tan inverse. Okay, so we take the tangent of both sides. Do we have any restrictions for the tangent function? I don't think so. We don't have any restrictions when we take the tangent of both sides, so we'll say the tangent of y is equal to x. Then we'll use implicit differentiation. So we have secant squared of y times dy over dx is equal to 1. Solve for dy over dx. Dy over dx is equal to 1 over secant squared y. Okay, and so now we have to replace secant squared y with its expression in x. So we'll use the principle of right triangles from your trig. Okay, so here's our right triangle, and we know that the tangent of y is opposite over adjacent. Okay, and so tangent of y is equal to x, so that makes the hypotenuse equal to 1 plus the square root of 1 plus x squared. Okay, and so what is the secant of y? Well, the secant of y is hypotenuse over adjacent. So secant of y is equal to 1 plus x squared. Okay, and so now dy over dx is equal to 1 divided by the square root of 1 plus x squared quantity squared, which is simply 1 plus x squared. Okay, so this is one that you need to memorize. The derivative of the inverse tan function is this. 1 over 1 plus x squared. That's a very, very important result. Okay, so how about taking the derivative of the arc cotangent function? So I will leave that to you. The formula is in the book, or you can look it up on the internet. So I won't go through that derivation, but because it's pretty much a repeat of this exercise. You identify the principal part of the cotangent function, which I believe domain will be on from 0 to pi. Take the first branch and then proceed accordingly. I think you'll get a cosecant. It'll be something like a function of cosecant of y or something like that. So I'll leave that to you as an exercise to compute. Shouldn't be too hard. But what's interesting is if we decide to take the derivative of the inverse secant function. So let's do that. So let's go back to our calculator. And let me remove these. So again, I'm going to leave it to you to calculate, be able to derive the derivative of the arc cotangent function. So erase. Okay, so y. So now we're going to calculate the derivative of the secant function. So let's start off by graphing y equals secant x, which we know is to be 1 over cosine x, right? Okay, so as you know, let me adjust my window settings. So we want x-axis labels in terms of pi. Okay, so here's the graph. And so it remains to identify the principal part of the secant function. All right, so what would be a good candidate for the principal part of the secant function? Say, perhaps between, in as much as that, let's try a negative pi over 2. Let's try this first. Okay, does that look like a reasonable? No, it definitely doesn't go through the negative value, so we can't use that. So let's erase this. So let's try it again. So y is equal to secant x, okay, shown in yellow and orange. So we need to zoom out somewhat. Perhaps if we chose, say, between maybe 0 and, what is this right here? Maybe 0, or how about, let's see, we're duplicating here, so we would want something maybe like this piece right here would go from 1 to infinity. So that piece will work, and then this piece right here will go from -1 to -infinity. So maybe we want those pieces. So let's try from 0 to what? Is that pi halves? The secant of pi, right? I think this would be pi. Let's identify this point, this local maximal here. What are the coordinates of this local max? Yeah, I believe it would be, yeah, pi -1. Okay, so we'll go with that then. Let's try restricting our secant function between 0 and pi. And I believe we'll go through our full range of output values. And we'll check that when we plot the arc secant function. All right, so I'm hoping this makes sense to you. How to identify the principal parts of a trigonometric function. You just explore it. Okay, so 0 to pi. If you don't know it, if you don't memorize it, I don't expect you to memorize it, but be able to understand it. So it looks like this definitely goes through the full range of the secant function, and it appears to be 1-to-1. Okay, and so now let's go ahead and verify our claim. So this is, before I do so, let me write it out for you. This is y is equal to uppercase S, the principal part of the secant function. Okay, kind of a strange looking function. And with this, we're able to take the inverse of the secant function. All right, so arc secant. Y is equal to arc secant x. Okay, and it's shown in black. Okay, and just as a sanity check, we'll go ahead and we know that function and its inverse has to be symmetric with respect to the line y equals x. Okay, and so it appears to be the case that we have identified the arc secant function right there. It is 1-to-1. It has a horizontal asymptote at what? At x equals pi halves. Okay, so let's plot that. So a horizontal asymptote at y equals pi halves, so shown in blue. Yeah, so you can see that the line y equals blue is a horizontal asymptote, whereas, yeah, y equals pi halves is a horizontal asymptote for arc secant, whereas x equals pi halves is a vertical asymptote for secant, principal secant. Okay, so there's your graph. So try to understand what's going on here in our computations for the principal secant function. So it's shown in black. All right, so now we need to calculate that. So so note with the secant function, the y values range between, let's see, how do we, okay, so this is pi halves, right? So this is the line y equals pi halves, so let's see here. We need to define where the output of the secant function is restricted to, or the output of the arc secant function. So note, and let's see. All right, so let's look at this again, another perspective. So note that the output of the arc secant function has two intervals, ranges over two intervals. This interval right here, let me accentuate it. So from 0 to this line right here, the arc secant function ranges from 0 to pi halves. Okay, And let's see, is that 0 to pi halves? What is the blue curve? Yeah, 0 to pi halves. Y is ranging from 0 to pi halves here. And then what else do we have? Pi. Is that right? Is that the right piece? I'm wondering. I need to check some more. This may not be the correct principal part. Okay, so we know we have 0 pi. Okay. So this is, I'm not sure what's going on here. It doesn't appear to be symmetric with the line y equals x. Let me check here. So if we go between pi and 3 pi over 2. Let's see here. Let me check. Check a little piece of literature here. I may not have the right depiction of the secant function. Look it up in a text here. Let me see what the trig book says. Yeah, I can never remember these. It's kind of hard to find in the literature what the okay, so let's try this. Oh, I see. Okay. Okay, so according what's convention, it's according to the trig book. Let me erase this. What I need to do is to identify the principal part of the secant function. That's the strategy. And so I don't want to belabor this too much, but what we need to do is we need to define the secant function between 0 and pi halves. So let's erase this. Erase this. So what I had was not the principal part. So that wasn't right. What I have to do is I have to define secant function as follows. The principal secant. Let's see if I can do this in this calculator. We need to go from, so let me take off this restriction. So y is equal to secant x, okay, and what's typically considered to be the principal part is we go from 0 to pi halves. So we go from 0 to pi halves, so x equals pi over 2. Did I not have that? May have had that already. Okay. All right, so we take, and then we go from x ranging from pi to 3 pi over 2. Okay, so let's graph x equals pi, and then x equals 3 pi over 2. Okay, so those will define our pieces. I believe we had that. Oh, I may have used this branch right here. So why couldn't I have used that branch? Why do they use this branch? I'm trying to think here. I originally said from 0 to pi. Oh, that's strange. Well, anyhow, what's convention, what I think mathematicians have defined, this is actually a definition. Okay? What I'm accentuating in green is considered typically the principal part of the secant function. So they call this the principal part. Okay, so we'll go with that. I had originally including this branch right here, and so that's not customarily what we'll use as the principal secant part, but I don't see why that couldn't be used. But nevertheless, the textbooks will offer that up. So now let's go ahead and plot back y is equal to arc secant x, okay, and that is shown in green. And let's see here, y is equal to pi over 2 will be the horizontal asymptote. That'll be shown in purple. And then finally we'll do y equals x to show the axis of symmetry. Okay, so let's see what we have here. Okay. Not much different from what I had before, really. Okay, so we'll take the principal secant function as defined. So let me write that down on the slide. Okay, so the principal secant, I'll summarize. Y is equal to principal secant x. Okay, and it is defined, the range. I'm sorry, the domain. Let's define the domain. What's used in my trig class. Okay, so the domain of the secant function will be the interval on the x-axis from 0 to pi halves, union pi to 3 pi over 2. Okay, so we'll call this our domain. All right, so the domain of the principal secant. So now this will become the range of the arc secant function. So now we can go ahead and calculate the derivative of the arc secant function. So let's say y is equal to inverse secant x, and we want to calculate its derivative. So now with this in mind, we have a piecewise defined function. So the arc secant function is defined piecewise. It's defined on this interval and it's defined on this interval. So now we have to calculate the first part of the derivative for y. And so, well, before we calculate the derivative, we know now that if we were to take the secant, so both sides, we have the secant of y is equal to x. And so in calculating this derivative, the first thing we'll do is we'll calculate the derivative of this for y contained in the set 0 to pi halves. Remember, we flipped the domain in the ranges, so this is now the domain of the inverse secant function. So we have to do this, and when we're on this interval for the arc secant function, x is greater than or equal to 1. Okay. So what do we have here? So secant y is equal to x. So now we take the derivative. Let's see here. So the derivative with respect to x, so we'll have secant y tangent y times dy over dx. Okay, so that's equal to 1. Okay, and so dy over dx is equal to 1 divided by secant y tangent y. All right. And so there's a trigonometric identity. From trigonometry, we know that tangent squared y is equal to secant squared y, secant squared y minus 1. So the tangent of y is equal to the square root of secant squared y minus 1. Now, why did we, okay, so actually it's equal to plus or minus the square root of secant squared minus 1, right? However, since we're differentiating on the interval 0 to pi halves, if you recall the graph of the tangent function, okay, recall the graph of the tangent function, and I'll sketch it briefly here. Like so. Remember the tangent function looks like this. And so from 0 to pi halves, the tangent function is above the x-axis. So that means we can drop the negative sign because we're differentiating on the interval 0 to pi halves. And also, the same result will hold for the interval from pi to 3 pi over 2. So if we look at the graph of the tangent function on, let's see, here's pi, and here's 3 pi over 2. 3 pi over 2 is a horizontal, I'm sorry, a vertical asymptote. Like so, okay? So on the other interval, pi to 3 pi over 2, for which the principal secant function exists, the tangent function is above the x-axis as well, so as you can see from this graph. So there's no problem with a negative sign, having to treat a negative sign. So the tangent of y is equal to this. All right, so now knowing that, it's really tricky, isn't it? So dy over dx is equal to 1 over secant y making sure I'm correct here. Secant y times the square root of secant squared y minus 1. Okay. All right. And so now all we have to do is replace secant y with its expression in x. So we know that the secant of y, which is hypotenuse over adjacent, okay, is that. And so let me see here. So the secant of y is equal to x, right? The secant of y is equal to x. And so all we do is replace secant y with x, and then we'll have the square root of x squared minus 1. Okay, and that occurs when y is confined to these two intervals. Okay, so all right, so let me check one thing here. I want to check something with the text here. This is actually problem number 64 in section 3.5. So let me check if I've answered that question. I'm looking up problem 64 in your text at section 3.5. Yeah, so we did 64A, and actually what I had originally was the solution for 64B. So yeah, so what problem 64 is saying is that there's not a consensus in what what the definition of the principal secant function was. So actually what I did firstly and erased was correct. We would have achieved the same result for the, almost nearly the same result for the definition of the inverse secant function. So let me see here. Is it worthwhile to go through that exercise to calculate the derivative of the inverse secant function? I think it is. All right, so let's go back to the way I originally had set up but erased for the calculation of the inverse secant function. Yeah, because I'm recalling now that mathematicians, there's a dispute amongst mathematicians as to what comprises the the derivative or the definition of the principal secant function. So actually, this is what we did here. This illustration was the more common usage of the arcsecant function. So, but we have to treat my case as well because it is a legitimate case, my previous case. So let me go ahead, put back in the graph of the secant function, okay, and we'll go ahead and see if we can pick off the principal part. So I originally said that this was the principal part right here, and this calculator used the other version. Okay, so why don't we use this as the principal part now? All right, so if we were to proceed along those lines and calculate the derivative of the arcsecant function based on this principal part, we're not going to quite get the same result. We'll get close, but nevertheless, there is a contradiction here in math. So I think it might be interesting to sift through it. So a revisit of it. So if we say y is equal to principal secant x, where now we have what? The domain of the principal secant function will be written as follows. We have a different domain for it. Yeah, that's why a lot of math, they sidestep this a lot in the calculus class. So the domain of the secant function x this time will equal to 0 to pi halves, and that will be the positive branch, union, and then the negative branch, like so. Okay, we will exclude pi halves. Like this. So this will be our new domain. In the previous exercise, it was, what was it? What did we say? Yeah, this was the previous domain right here. Okay, and that's valid. But what's also valid is this different domain. And so now let's calculate the derivative of the arcsecant function here. All right. So we're going to make use of the identity again, same as before. Tangent squared y is equal to secant squared y minus 1. Okay, but the thing is, what happens now is that the tangent function is plus on this interval and minus on this interval, so that creates a different kind of challenge. So tangent y then is equal to plus or minus the square root of secant squared y minus 1. All right, so we have that. So proceeding on the intervals 0 to pi halves, let's calculate the arcsecant derivative. Okay, and on this interval, for the principal secant function, x is greater than or equal to 1. And of course, tangent y will be greater than or equal to 0. Okay, and so we have secant y is equal to x. Then we'll have secant, taking the derivative with respect to x at both sides, we'll have secant y, tangent y is equal to 1, dy over dx is equal to 1. So dy over dx is equal to 1 divided by secant y tangent y. Okay, and since we're on the interval 0 to pi halves, the tangent y is positive. Okay, so we'll have 1 divided by, so if we're on the interval from x equals 0 to pi halves, then the tangent of the output of that particular x. So let's see. If y is between 0 and pi halves, then the tangent of that y will be positive. So we're left with secant y times the square root of secant squared at secant squared y minus 1. Okay, which is equal to, that's not a minus 2, that's a plus 2. So that's equal to 1 over x times the square root of x squared minus 1. Okay, and the secant y, of course, is positive on the interval y equals 0 to pi halves, and so the sign is correct. All right, so now that remains to check for pi halves to pi. Now, looking at our graph, can we go back to our graph? Did I lose my graph? Let's see. Where was my graph? I must have lost my graph. Where's this? Yeah. Okay, now, looking here, okay, so this is the line y equals pi halves. So from pi halves to pi, we see that the secant function is negative, all right? So the secant function is negative. So let me go back here. Where was it? The last slide I was working on. Okay, so now we need to calculate the derivative of the arcsecant function or y equals pi halves to pi. And so what happens is it's still the same thing, but we have a problem with the sign. So how do we deal with the sign? So did I lose my internet? Okay. So now for y in this range, okay, the secant function as well as the tangent function are both negative. Okay, so that means what happens is the derivative will become, when we do these calculations again, we'll have 1 over x, we'll still have the same output, okay, times the square root of x squared minus 1. But even though the product of these two factors will be negative, we'll still have the product of two negative numbers being positive, we'll still have an output that's greater than 0. So so here's the dilemma we face with the arcsecant of x. So we can summarize here. We can say that for y equals arcsecant of x, okay, the derivative y prime is equal to 1 over x times the square root of x squared minus 1. Now we have to be careful with this because for some values of x, okay, in particular for negative values of x, the arcsecant function, so let me write this down. Note, for x less than 0, arcsecant of x is greater than 0. Okay? All right, so if I were to, so let's look at this equation for the, what we've derived for the derivative of the arcsecant function. We can see that if we were to plug in a negative number into y prime, the output would be less than 0. So how do we guarantee that when we plug in a negative number for x, that the output for the derivative will be greater than 0? Well, the way we deal with it then is, since we want to assert that for any value of x, the derivative of the arcsecant function is above the x-axis, is we do this. We replace x with the absolute value of x. All right, so that means no matter what value of x you plug in, the arcsecant function is guaranteed to be positive. All right? Okay, so that's it. This is the formula you should know and be able to understand. So if you have any questions about this derivation, let me know. And so we basically now we have two formulas for the derivative of the arcsecant function. It just depends on which domain you've chosen for the arcsecant function, or for the principal secant function. It all depends on the domain. So it's a complicated proposition for this. This is kind of an advanced problem. Really test your knowledge of trigonometry. So I'm going to stop right here for this lecture on section 3.5. I'm not done with it yet, so in the next video lecture we'll work some more problems, some word problems, and talk about more about implicit differentiation. Okay.